It is what it is. Hey, Coffee Compiler Club, just a couple people today. I'm going to talk register allocation. We're being recorded. It's all good. Let me find the share button. I was, in fact, going to talk register allocation anyhow, because that's what I've been working on. Hey, Derek.
Hey.
Um, yeah. So I don't know which piece you're interested in particular. I was going to do an overview, but I can do a particular piece.
Yeah, so can you just do one example and just go through it with the debugger, just to see,
Yeah, what's
uh,
going on?
yeah.
So I
So maybe,
grabbed, go ahead.
yeah, so maybe just one of the floats, or I don't know, maybe the one at the top.
Okay, I can do an even simpler one here, although it won't show off a bunch of stuff here. So let's go do, like test basic one, right?
Yeah.
So like first thing, I'm gonna look at the code. And this is no, I have a bunch of dumps and for the register allocator and popular with me is different print for the different pieces of the compiler you're debugging. So this one is standard node dump. There's a main function entry. There's a memory argument, return program counter. There's just an or immediate. It's not showing the immediate value, but it's just going to or a two onto it and then return the thing. So node number 7 is getting returned. Argument is a node 8, which is the input to the ORI. The argument and the return register disagree on register numbers, so a copy has to be inserted. It must have a copy. Um, so then there's a register allocator. I went ahead and ran up to it. The other dump for the register allocator is the ASM dump, which only works after it's actually done some steps. So I'm gonna walk through. So the big one was graph color that builds the live ranges, builds an interference graph, attempts to color, except it fails early. Um, so I have failed. I'm going to go look at the failed list. The failed list is a live range. So live ranges fail. And that means for some reason, I was unable to color this live range. If I go look at what the live range is, it's live range number 1. There's a union find hack going on. Let me widen this up here. There's a union find hack going on to make live range discovery fast. That didn't apply here. No register was allocated. There is a one register def and a one register use. That means there's at least one point where the live range has a defining value that was pinned to a specific register. That's parm x86. The incoming argument is pinned to a register. There is a single use. There's a use of a single pinned register, and that is also the return. And it's index number 2 in the return. So if I go to these guys and I go ask the mock def and I say, give me your outreg map, he says RDI. I have to produce a value in RDI. That's the calling convention for the incoming call. And if I go to the use side and I say, give me your reg map of the U index, which is 2, he says REX. So both of these things come straight out of the portability description for those particular guys. So where do these things come from? Let's go find return. Return says, check the signature for a float, and I'm either returning you a normal register or a return mask. If I go to return mask, it's just REX, and that's the standard calling convention for both Windows and System 5. And we're doing System 5 here. Projections go ask the question recursively of their input for outright map index. This will go to a function header, um, which, let's see here, is fun x86. I don't have it loaded here. Fun x86, chapter 20. He says, oh, I'm going to default to, oh, that's interesting. Where did he get it from? Oh, I didn't even have to go there. Why do I not have to go there? I claim I should. Oh, I went to parm, not projection. I went to parm. Yeah, you go to parm. And he just goes to call and mask. and takes the function signature. So call and mask has a function signature and an index, and he does a length check on the standard, and he does a calling convention check. So we're going to go system 5 mask, and it's the first guy up, so it's RDI. So there is this set of places where we pick up these register constraints from. The parameter picks it from the calling mask for system 5. It says REI. Fine. The return is an REX. The live range claims these have no registers in common. The register mask is empty, and therefore he's going to fail, and you're going to go color. So going back to where I got here from, let's go find the fail set guy. Where's my fail dude? Why am I not finding fail dude? Here it is. I'm going to rerun. I'm here at the start of the allocator. I charge forward. I hit fail. It failed live range 1. Where am I at? I'm in build live ranges. Let me close some of these things here so this shrinks up a layer and I get some screen real estate back. So what's going on in build live ranges? So build live ranges computes live ranges in a single forward pass. What's a live range? A live range is a set of defs and uses that are pinned to the same register. They can be pinned to a specific named register as well, like in the case of a calling convention where I have to have an incoming argument RDI. But the general rules are same register. So why would some set of unrelated things be same register? It's either fee functions or it's two address operators, like the or immediate says the input and the output value have to be in the same live range. So somewhere in here, I'm going to go compute these things by, for all basic blocks, for all nodes in a basic block. If you're a machine node, if you're not a machine node, you're something like a fee function or whatever. You don't have an issue for fees fees do, and they get handled down here. But there are a couple things like control projections off branches and things that don't have registers involved with them. So there's a define a live range. This guy just goes and makes one of these instances of this thing, gather some shit. If you have no mask, you're not interesting. Otherwise, if you're a two adder, then I can go get your live range from your input, which has to be done already because this is a forward pass. And he'll have a live range. And you have to be the same live range because you're a two inputter, a two addresser. Otherwise, you make a new one, and then I gather a bunch of data on you. Like I found a defining point, and the defining point may have size 1 mask. That's interesting. So a lot of things in Allocator do special for size 1 masks because they're really common. And then I'm going to gather up the and masks of every other thing because I'm trying to compute the limit, the constraint, the list of constraints of all your defs and uses. And this might fail right away if I just have no masks or no registers when I'm done. In this case, though, after I define, I run through the other direction. So def, you made a live range. Now you go look at your inputs. You have an input. The input has a live range. It did or it didn't. Sometimes you have like an anti-dependence input, no live range, but you get a live range. That means you have a register mask. That means I would your live range and I accumulate a register mask constraint. And in this case, that constraint ran me to 0 and I fail. So I have two constraints here, the def and the use. I got to fail out of them. Let's go rerun this in the debugger and then we'll stop and we'll spill it. So here's going in again. I'm at some particular live range in. It's going to be in as a function header. It's going to be one of those things that has no live range mask, no register masks with a function header directly. So nothing. Let's try again. Here I am on a parameter for memory. Memory again has no mask. I don't care. Here I am parameter for R. This one is exciting. I'm going to come through and say, do you have a mask? You do. It's RDI. Are you two input? No. Let's see here. No. Return 0. You're not. We'll make a new live range. Go make the live range. It just picks up a magic instant live range number and sets his initial register to like I don't have a register. And then I put you in a mapping table, mapping between parameter and live range. So when I do this mapping table thing, I'm effectively taking a node in the graph and extending it with a new field that's kept in the side array as a hash table. That happens a lot in a lot of different places, so I don't want to make a billion fields on a node. So I do this side array. But now I have a live range associated with a node. and then I go add a bunch of stuff to it. Is it size one? So just check the bits, size one bits. The answer is yes. So here I am gathering. I have a def point. I'm going to assign it. I have a size one def, so I'm going to assign it. It's not a split instruction. I collect those for spilling purposes. And I didn't fail because that live range picked up a mass to RDI. Then I go to your inputs for this guy. There won't be anything exciting there. So let me go ahead and run a little bit along until I hit the other side of things here. Okay, so here I'm at the ORI, and he both defines and uses a value. And I roll through the define, but he will have already had a value. So when I go over here and I ask, he would have found you already, where he probably would have said to adder and said, go to lurge2, which would have said, go to find the lurge, which goes to say, go get, and if you find it, you got it, except there's a union find rollup thing that didn't happen here. And so he defined the input for the live range. Um, and now he's looking for the other direction. So he's saying, check my inputs. Now check my uses. Oh, I can be anything I want, except it's going to be two inputters, so I have to match. But I'm going to ask size one question. So here I have a use at the OR of live range one, and he's like recording the first use. So he gets his first use. It's not size one. It can be any register he wants. And it's not a split op to be saved for splitting purposes. And, that's easy. He's done. It's all good. So basically at this point, I can claim live range one could be an RDI, and it's an OR op that would OR some immediate into RDI. That's perfectly valid allocation so far. Keep going. I'm running along. I found the return op. So I'm now doing the return. It's a user of this value as well. So I got a mask out of it. The use mask is RAX. So when I come in here, I'm going to say, I have a single user and it's size one. So I'm going to overwrite my old one. Now I have who is size one on the use side. And I'm going to record that I've got one of those. And it's not a split, so I'm done. And then I go here and mask you, and I say, oh, I have these two masks, and update in place and mask, and the mask been empty. I just do an and no mask, no registers, it's empty, it's a fail. That's why we failed pass one. Okay.
Yeah, why do you need to do a bitwise and there? Because I
Because I'm collecting the set. Like I might have, like if the ORI didn't come from parameter, but came from some other calculation, it could be in any register. So it's got 16, 15 register choices. Then it gets used by the return. The return says, I have to have an REX. So you need to AND your 15 choices. It's a pile of bits, 15 bits, with the one bit for the REX. You end up with one bit left over, REX. But it could be that I've got other constraints going on. And so I keep subtracting register constraints from the list of registers from the list of choice registers until I've collected all those constraints. In this case, on an x86 of the modern era, mostly calling conventions, pin registers. Some of the multiplies have CXDX, I think. And I know the shift has CX. And those are like a limit of the pin registers. In times past, there were more pin register things happening. And other machines, you might have other constraints where you're allowed to use the left-hand side or the even odds or whatever the constraints are. Like in the old register pair land where you only had 32-bit registers and you wanted to make a long or a double, you had to pick even or odd sides only for some of the operations.
yeah, so
Okay.
if it fails, then you're gonna start spilling, yeah? So you're gonna
Yeah.
start
Yeah.
doing heap allocation or putting something in the stack or something like that.
Well, it's all going to be stacks. So spilling's only ever to the stack, it's never to the heap. Let me try again here. What did I do?
So does every single machine node have to define the like a specific spilling function that is gonna use for the spilling kind of thing or
Yeah. So we'll do that right here. Okay, so round one, I went in, I failed on building live range. So he just pops out. He doesn't do interference graph or coloring. He's just done. Now he goes to split. So split says for all the failed live ranges, go do something. Here's live range one. He's going to start asking questions about live range one. So this is a case where I have a split empty mask. This is a case where I have a direct hard conflict. Somebody demands RDI, somebody demands REX, can't happen, must split. So now I have to figure out how to do a split. So I'm going to go through here and say, oh, I have a short version. If you took a single guy who is defining one register and a single guy is using another, and this is a common scenario, then I don't have to do spill everywhere. I'm just spill once at the def, once at the use, and maybe only once between them if they're just directly connected. And that will break up the live range and allow flexibility. And then when we color, we might get rid of one of the two copies. But I'm going to copy in here. So how do I get a copy? A split. Well, I call the machine code.mock. That's machine. So let me get rid of some of these things here. Why you can go away. That gets me, thank you. And that gets me a better, yes, shorter file. Okay, so what happened here? I went to undercode, under mock. We come back up. This is a machine. This is the machine I am using for the CPU target. That machine has to define a split up. It only has to define a handful of things, but one of them is how to spill. Okay, there are two implementations, one RISC, one x86. Here's the x86 one, make me a new split up. What's a split up look like? Says I'm a split, I'm a standard machine node, I have a full register mask. So the requirement on splits, is they can go anything to anything, any register, and they can go, and some of those registers will be stack slot registers. And the encoding can be complicated or different. So the encoding for a spill to stack is a store, spill from stack is a load, spill in the flags, maybe push flags pop into a register or something weird, right? The encodings can be bizarre, but you're going to do any register to any register. This is this is the RISC allocator's get out of jail free card. So he says, I need a split. Now I hit insert after. What does that do? It's a stupid piece of nitpiddly thing that's going to run through, find the instruction in question, and insert it in the graph in a particular place. So I'm already a place where I'm in fixed locations for where things are in basic blocks. So the users of a control flow point are all fixed in location and in order. So here I am at the fun. This is my control flow header. I have a parameter for memory, args, RPC. I just stuck a split in. It's in between the OR and the ARG, and it has any to any register mask. Same thing for the after side. I go just before the pinned user, the constrained user. Go look again here at my basic block. Where did I lose the easy view of it? Probably up here. No, it's not. It's because this guy, I could sit here. So now this guy has got the parameter, a split from the parameter of the OR, a split between the OR and the return. And that was spilling for that guy. So if I come out of here and I get to here and I go to this dude and I look at this view, you'll see I have a split in here and a split in there. So does that answer where you get those splits from?
Yeah.
Yeah, fine. Okay, so then we go again. And now we're going to come through here. And I'm going to run through build merge, and I didn't fail. So I could go do interference graph building. But let's go look for a second at the other view, which will be the ASM view. The ASM view is smart about live ranges. So, and he hides other things. So then he says, I have an argument. It produces a live range V1 that's copied to live range V2. V2 is set to V2 and the or immediate, and there's a V3 and a return. Okay, so those are my three live ranges. Now I have three. I used to have one, now I have three because I broke that thing up twice. If I go look at the set of all live ranges, here I have my three guys. You can see live range 1 is pinned to RDI. Live range 2 is completely free, any register. Live range 3 pinned to REX. So we're ready to go for interference graph building. The interference graph is really dumb and trivial here. The algorithm is a little more complicated, and we don't show any of it off for this work. This is just like throw everything on the work list and then call do block until you get done. There's like one block here. I'm at the block. Or maybe the stop counts as a block, and then the start, function starts. Okay, and then having gotten a block with something in it, the function header block, he has his outputs. You walk backwards. So this is a backwards walk. So this is a classic liveness analysis. You call do node for every node. So here I am at the return. The return doesn't produce a live range out. It consumes a live range. So it has nothing on the defining side. When you're rolling backwards and you define a value, you just killed it from below. Somebody who was looking for it up just found it, and that's why it would be killed, but the return didn't do that because there was nothing there. Interfere with everything live. There's no live range to interfere with yet. Now go make things live. So count through your arguments for the return. You got a memory, it doesn't do anything, it has no live range. You got a def for split. He gets a live range, it's V3 RAX for the return. He asks the question, do I self-conflict? I don't have any self-conflicts in this example, so I guess I'm just going to ignore that so you can see what a self-conflict is. Then they're going to look to see if you have a single must-use register which conflicts with some other thing. And if you do, I'm going to yank the register out as opposed to allow you to conflict. So right now, live range 3 is in RAX. Live range 2 has all registers. These two would conflict in the interference graph. They would get an interference because you can't pick RAX for live range 2 or you'll not be able to allocate live range 3. So I'm going to go ahead and grab this mask. I see it as size 1. I'm searching the live set. Oh, there's nothing live at the moment. Oh, I see. It's not because I haven't even hit 2 yet. Yeah. All right. That'll happen in a minute. So I make live range 2 alive and then go again, grab the next guy up. And the next guy up is the def RPC parm here. And he's like, oh, I'm walking the return guy and there's nothing going on. And that was the last for the return there. And then we'll go to the next node. And the next node is a split. This will make a live range alive. No self-conflicts. Having made this live range alive, I don't need it. It doesn't live anymore. So I just have a split that makes V2, V3 defined. So coming up from below, it is now defined. The return gets its value from the split. The live range 3 is no longer alive going up. There are no more users of live range 3 above me in the backwards walk. It's a split, so I can remove an instance of where you would otherwise conflict. Now go look for everything else that's currently alive with live range 3. I think there are none as usual. So I get nothing, and that's the end for that input. And he has another input. I'm doing all the inputs for live range for the OR. And he says, I have an input live range 2. And now I'm going to check for self-conflicts. There are none. See if I have a single def live range here. I don't. Make it alive, carry on, and keep doing backwards walks. So this is going to roll backwards through. At the end of your basic blocks, you'll have a set of things live. You push them into the live out set of prior blocks, and you loop that until you stabilize. This particular graph is quite simple. So I'm just going to run to the end and take a look. Where did I got? Where I got Allocation? Here, what's the, oh. IntelliJ could definitely be smarter about that. Nothing happened to here. I haven't done any allocations. I didn't break anything. If I go look at the Standard guy, he says nothing's happening exciting there. If I now go look at, uh, wow, there's no interferences because this piece of code has no interferences. So the interference graph is completely empty. So there was success, go color. So it's very boring live range, very boring coloring as well because it's such a trivial thing. Um, the first set is gather all your live ranges and move them from bit sets into adjacency lists. The bit sets are empty. The adjacency lists are going to be empty as well. Let me go find my live ranges. Not IFG, I want alloc. Live ranges. Here they are. He says adjacency list is null. I have no neighbors. Adjacency list. No, no neighbors. Adjacency list. No, no neighbors. Geez. Okay. So this is all going to be trivial. So over the color stack, you grab everyone who's trivial. All my 4 live ranges, they're all trivial. So I have this thing here where I say, I'm starting from 1, it's trivial up to 4. I'm just going to pick a color as available. Grab a live range. Here's V1. It wasn't a risk or an issue. There are no neighbors to yank from the graph. Yanked, carry on. Full live range V2, yank, carry on. This is all very boring. You can't see what's happening because there's no interferences. Go in reverse. You reinsert people in the graph. Here's a live range. It's currently got a mask limited to RIX. Check your neighbors. There are none. So you get to keep your mask. It's a full, the mask remains the same. Pick the first color. It's RIX. Try to do some biasing. There's nothing to be done because you don't have any extra register choices. So you got RIX and they're done. Go to the next guy down. He says, I got no neighbors. I'm going to go pick my rig mask. I'm going to go pick my color choice. I'm picking REX. So it's also done. And I'm going to hop out of here. And this graph is done. And now we're going to post color. But before we post color, let's take a look. So from RDI, move to REX, or yourself into REX, move REX to REX, and return. And then post color yanks the empty the junk move. And so if I look again, we'll just have the junk move done, and he's done. And this graph is too easy. There's like nothing exciting going on. So there it is, the whole program allocated. Boom. And like I said, it's very, that one is, you basically got no choices about anything, and there's nothing to be done. So it just goes in one pass with no excitement. So I can do an allocation guy. This will be a bigger thing because he'll have a new, which requires things, or I can do the float guy. The float guy demonstrates what happens when you have self-conflicts. Because he has 2 values, he carries at a loop carry dependency through the body. And because of that, his first cut is everyone joins one big live range, but guess and next conflict. And you get a self-conflict, and he has to split for that. Then he gets other things that are all color easily because he's got, 16 registers and, for FP, and it's all done. So why don't we do that and look at self-conflicts because those are maybe less obvious what's going on here. Run, boom, start. First thing always, go look at what it is that we're doing here. So there's a main, an arg, and an RPC at the start. There's a 0.5 constant. There's an int to float that takes number 13, that's your argument, and turns it from an int to a float. Then we're in the body of the loop here. The loop has a phi function, which is your guess. Takes the int, originally takes 15 as the back edge. 15 would be a mul f. And then you take the dude and you divide original value over your guess. So guess is on the right, original value on the left. That's the int to float converted thing. And then you're going to add that to your guess. So guess on the right, divide on the left, and multiply it by half. And that's the new value. And before you get there, you compare yourself to see if you want to jump. And this print has a layout of the nodes badly done for no good reason. I can do the other print, which will have them in order, but doesn't have any live ranges, so it's not very exciting either. So that's the sort of standard set of things. In the original code, if you saw, there was a copy. So go back to the newtons. There's a copy right here. Gas equals next. And if you go look at the SSA form, there's no copy. So what happens here is you can't get away without a copy. You must have one. So the allocator will fail. And when he fails, we'll see why, and then that will be a self-conflict. He'll force a split in. He may have other splits in the beginning as well. Let me go find my fail point and watch where I fail here, just so I can see the first failure. So, okay, go to graph coloring. We're going to walk through. We're going to build live ranges. So no failure while building live ranges, which means I can immediately go look at the live ranges and see how they look. So take the I to F, convert, argument, live range 1 comes as an int, converts to live range 2, which is the float version of the same thing. So live range 2 has a guess. Live range 2 divides the guess by the initial value. Oh, look, there's a conflict right there. This is either this or this. And why are they all fused together? Well, because the feed function said, hey, fuse both my inputs and my outputs. The div said my output, my input. The add says output, input. These are all two adder ops. So they're all forcing everyone to be fused together. So I clearly have a broken situation. I can't be comparing self to self here. It's supposed to be two different things, guess and next. So it's broken. So do you want to go through and watch how build live ranges builds? Because he will force all these things to fuse together because they must to match the two address semantics and the feed function semantics. Or do you think you got why they're all fused together?
Oh yeah, we can go through the live ranges.
Okay, then we'll go through it again here.
So where is the self-conflict again? If you just go back to the source code, like where is the conflict that we are trying to solve here?
Okay. This is because in this version of things, because it's not an SSA form, you have a copy for a loop carry dependency. Let's see here, my wife's trying to reach me. Let me make sure it's all good. I think it's all good. Okay. But in the SSA form, the copies all disappear completely because you just directly push one thing to another. It's just, the renaming happens. You have no copies anymore. Okay, when you come back out of SSA form, sometimes you must have a copy. This is a case where you must have a copy. So you can see where I'm asking, does this make sense as to why you see a copy here, but you don't see one when I go look at the
Uh,
the
no,
SSA form?
I still don't really get why we need a copy there. Like,
Okay,
um,
so let's go look at this is now standard C code, Fortran, Java. It's it's simple code. If you don't have a copy here, the program's wrong, right? So how Newton's works, he makes a guess, he computes a next better guess. There's an exit test. Oh, I got the guess I wanted, so I'm out of here. I made no progress on the guess. It must be the square root. Or I need to go move this over to the next go round. So right here, I have two different things, next and guess. They're different things. I have to compare them for equality. Okay, after the words, when they're not equals, I go ahead and assign next, which was known to be different than guess because I just tested. It has to be different. So I assign it to guess, and then I go compute a next value. And I keep my guess so I can have my test. So I have two different values here. So that's why when you write this code, you have to write it with a copy. Like there's no way to write it without a copy. Do you see this?
yeah.
Okay. When you go to the SSA form, it's without a copy. And that's because I'm rolling guess into next as part of the normal SSA renaming things. And so the value for guess at the head of the loop here picks up the divide by 2, multiply by half, down here without using a rename. It's as well, everything is renamed uniquely every time. So the thing that you're calling next here has been named node 15. And the thing you're calling guess is at the top of the loop is node 11. But the phi function just takes node 15 and makes it node 11. Effectively, there's where your copy went. There's no copy in the SSA form. And this is, by design for every SSA compiler on the planet loves the no copy thing. That's the beautiful part of the beautifulness of it. But when you come out of SSA form, yeah, you're gonna need copies. Are we caught up on that piece? What happened there?
Yep.
All right, so we'll just go build the live ranges again here. I'm gonna go into a couple places and set breakpoints where things get exciting. So def, if you find somebody to def, and this is where you gather constraints. Okay, the next piece is here where the fee will be unioning folks, and there's another def which I already picked up, and then we'll stop when we get out of here. Guess we'll stop here. See what happens here. Okay, so somewhere in the world I found a parm. It's an incoming argument. It's not a two-outer. I'm gonna make a new live range for it. It's live range 1. I'm collecting. Live range 1 has to be an RDI. That's your incoming argument. Done. Okay, now I'm in the I to F guy. This is where the excitement just begins. It's not considered a two-adder, so he gets a new live range. His live range is allowing all your floats. This is great. He collects a little information in case spilling happens later. Nothing, carries on. Okay, now I'm at a 0.5 immediate constant. It's going to get live range, what, 3? It can be in any register. I don't care. However, I get immediate float constants. That may be a thing we have to sort out on x86, but I think we were good with it. Okay, wait, what? Union? Where, what? We hit the fee function. I jumped ahead a bunch. Okay, what happens to the fee? The fee says I need to claim that my inputs and my output all have to be the same register. Whatever register it is, it's all going to be the same, inputs and outputs. So if they're unrelated live ranges, I better be merging them all together. So I go take a pass and look for whatever live ranges I find on all my inputs and outputs. And I find live range 2 is one of my inputs. That's the initial value from the I to F. And I'm now going to do what's a union here, except that the union is going to say, I got nothing for the other guy, I bet you. Yeah, so it's a null. If I come down here, I have a null cut out. So I don't know if I'll actually end up with a union. Set the breakpoint where it counts. So he says, hey, the def for the fee's def itself is also live range 2. I have live range 2 coming in. I produce a live range 2 out because it has to be the same register. Go walk my other pieces. Do I find any pieces? No, so I went ahead and forced them all with the union here. So let's go look at that here, see if I can go, see if this will show me. So in the middle of trying to do things, so live range 2 comes from I to F of live range 1. The floating load is live range 3. The fee is live range 2. Immediately, I know that the def is this live range 2 divided by this live range 2, which is here. And the add's going to take out of the def at live range 2, and I haven't sorted the add out. But the output of them all has to be live range 2 because it's going to feed back in. So I've sorted a bunch of things here, but I'm only halfway done. But I've made the fee, the input to the fee, I to F, the output of the fee, which is what the mole is producing, all be live range 2. Furthermore, the fee as an input to the def, to the divide, is live range 2. And the divide already has an input from I to F, also live range 2. So like I'm already screwed. And the masks are not empty, so we're going to carry on. And I'm down here in the divide. Oh, it is a two-adder, so I'm going to go the other side and say, whoops, no, come on, step out and back in. And say, go get the live range for the other guy, which is live range 2, and I need to union it with myself, which is going to be, it's just a self thing. So he's going to say, yeah, I don't have any excitement. So I'm live range 2. The union find only really kicks in when you have really big, complicated programs like brainfuck shows up, but it's not happening here. But it just became live range 2 as the output of the divide. Um, Running along, here's an add to F. Same thing. It's going to say it's a 2 adder. My input's live range 2. My output's live range 2. Great. Here's the mul. The mul is going to be 2 adder, live range 2 in, live range 2 out. It's already pinned live range 2 out. No problem. Well, I got to compare. He's going to produce flags out. He's going to get a new live range 4. It's going to be flags. Great. And I'm done. So I ran to the end, but now I have this horrific mess where everyone's all in live range 2. And a little cleanup here where I'm just going to forcing a union finds. Actually, none going to happen here. So I'm done. So I built live ranges successfully. The only one of interest is live range 2, and it's everything everywhere. So we're going to attempt to build an interference graph. And while we build the interference graph, we're going to detect places where an input demands a certain thing to be live, but that same live range has something else also alive. And we'll have the same live range being alive twice with 2 different defining points. That's a self-conflict. So let me go, if I just run, I'll just hit it. And then I can go back up the stack and find things on it. Let me just go run, go hit it. So here's the fail. Live range 2 just failed. Why did live range 2 fail? Well, I'm in this suggestively named self-conflict guy. What self-conflict means? It means there was some prior definition, a phi, and a new definition, a mul. Both are alive at the same time. That's a conflict. And I flag it in the self-conflict flagging. Let me go back up another layer. How did I get here? Well, I'm busy trying to define live range 2, and I'm busy trying to define it with this mul, and I find another def. I guys say, oh, give me what's currently live for this live range. That becomes prior on the next layer down. And oh, there's 2 things live, and they're different. I'm screwed. So going back up again, how did I get here? I'm walking the nodes in the graph, and this is this backwards walk for nodes, and I'm looking for the input to somebody. I have a compare. The compare needs the result of the multiply. Turns out that the last step of the multiply, the multiply is the last step, computes the next value to guess. So at the time of the compare, I need the next value, but I need the guess value too. I need them both at the compare, and they have to be in the same live range, same register. I can't have 2 different values in one register. So self-conflict. So does that make sense?
Yep.
Okay, because that's a kind of a tricky one for a lot of people who haven't dealt with the graph calling register allocators. You get this self-conflict thing. Okay, now that I've got a self-conflict, I'm going to run on out and go look at splitting here. Make sure I got my breakpoint set. I do. So he's going to fail live range 2 a bunch of times for different self-conflicts. And I'm going to bail out here and say, oh, you weren't successful. Time to split. Let's go look at how many live ranges I have. I have just the one, live range 2. Well, it's the whole thing. The entire program is live range 2. Not quite, but that's the only one who splits, but it's got issues. So coming in here, I'm going to ask questions like, do you have a single def, single use? Can I break you apart in a way that gets rid of a register conflict? Like at this point, I'm not checking for self-conflicts. But he says, no, you don't match the pattern of somebody who had a definite use that had RDI, RAX, something else is going on. So I'll check self-conflicts. And I say, oh yes, self-conflicts. So let's look at this live range. What data did I gather about the live range? Well, I gathered a sample def and a sample use. And I noticed that the use was in fact pinned in XMM0 because it's a return of a float value. And then I I looked for splits. There were no prior splits. I haven't spilled this guy. And I have a self-conflict. What's a self-conflict map? Well, it's a list of guys who are involved in a self-conflict either on the def or the use side. So here's a def of a value that's being used by the phi, and here's a divide, and here's a mul, and they all are involved in a self-conflict somehow. The mask is not empty, so I didn't spill for running out of registers. I'm spilling for self-conflicts. Now I have to do something tricky about that. So I'm going to walk my self-conflict list. I'm going to put a split after every def and before every fee except just on the fallen side, not on the back edges of loops. So why this? Well, I need to break them apart always at fees, but sometimes because of two adder, I need to break them apart at two adder places where I'm forcing two things to be the same value, same live range, because of the two adder. This is a op equals of that, but I need this value and this value, so I have to split in between them so that I keep the old value and I update it in place for the second half piece. So that's why this set of splits goes in. So I'm going to come out of here and say, I did the split. That was the only live range. I've done those splits. Let's go look at the program post splits. So here I say I need I to F got split and I get a split again. And that's because different people split for different reasons. One of them is because it's a def of a value. One is because it's a fee use. Took the split. I have the divide. After the divide, I go ahead and split it in case I need the divide separate. I have an add. It turns out the add wasn't in my list. I have a mul. The mul was in my list. Where is the user of the mul? Here is the split for the mul. Here is the use side split on the fee. So 1, 2, 3, 4, 5 splits went in, 3 in the inner loop. So self conflicts put a lot of splits in. And this is one of these tensions where in C2, there's get the job done and get the code compiled versus how good the allocation is. If you split slowly, you will get fewer splits. And when you finally get a coloring, you'll have fewer spills in the end. And the spills cost money, cost time. Um, if you split aggressively, you'll color in one pass, but you'll have a really lousy allocation. And that will cost you in performance when you run through the billion splits. So you play this tension game of more splits or less. Here, because self-conflicts are hard for me as the allocator, implementer, engineer to figure out the minimal set of things that would free it apart, I go ahead and I gather the things that were involved and I split after everyone. And this guarantees I won't have this self-conflict again. And typically, if I don't need all those spills, I will be able to bias color them away. So that'll happen later. Let's go past here and say, let's go run another round of things here. We're going to build live ranges. I'm going to claim, let's go ahead and get to the end. Yes. So I built live ranges. Let's go look at that. Hello, what did you do? IntelliJ. So what do we get here? So I still have all my spills. So, live range 2 from the I to F goes to 4, goes to 5. Here I'm at 5. 5 gets copied to 6. I'm dividing 4 by 6. I move it to 7. I add 7 and 6. I multiply by half. I move that back to 5 so I can be back around here. I'm comparing 5 and 6 and yeah. So a bunch of live ranges here, but they're broken up pretty nicely now. So maybe things can be, colored regionally. Let's go over the interference graph. Okay, so we didn't get a fail out of the interference graph. That's nice. Let's go look at it. Where's a good way? So I have all these live ranges. RDI for V1 gets RDI. Everyone else, oh, their return in XMM0, there's some flags. Everyone else has pretty generous masks. But I want the interference guy, which I now here. So I should have built an interference graph. Okay, so this interference graph is an array of bit sets. It says live range 2 interferes with 3. 3 interferes with 4, 5, 6, 7. 4 interferes with 5, 6, 7. 5, 6, 6, 7. So that's what I built. Let's go look at the program again. What do we got here? Oh, Alec. And this, if I can move this guy away from, you can see, no, how about now? It's like pixel perfectly accurate. That's not helpful. How about this? How about now, brown cow? Okay, kind of, sort of. Yeah, okay, here we go. So live range 2 conflicts with live range 3. So 2 is alive here and is consumed down there in the blue area with 3 in the middle. They clearly conflict. Okay, here's 3. Where's used? 3 is used down here, but it's actually carried over the entire body of the loop because it's carried around the loop. So 3 will interfere with everything in the loop and everything above it there. So 4, 5, 6, 7. It doesn't interfere with 8 because flags and XMMs can never overlap. So I don't have a 8 and 3 interference, but 4, 5, 6, 7, yes, definitely interferes. Okay, so that's 2, 3, 4. Where's 4? 4 interferes with, well, it doesn't interfere with 5 because he's directly copied, but he interferes with 5 here. 4 is used here by the divide. It's the original value that you're dividing from every time. So 4 is also going to carry through the body of the loop. So the divide keeps using it over again. So 4 conflicts with 5, 6, 7, and not with flags on 8 there. Let's get 5. Oh, shit, I got to reset this thing. Maybe. No, it won't let me do it. You bastard. It's weird. Yes, it fails on me. Look at that. And there's no drag in it. Oh, wait. I had it. Oh, it's 1 pixel. Fine. Okay. So 5, where's 5 go? 5 is here. Then 5 is done, except it's redefined here. So 5 has this hole where it's not alive. 5 is not alive in here. That's the original guess value. And then, oh, no, it is. Oh, no, no, no. This is the next V6. Yeah, 5 is not alive here. 5 is alive above. 5 is alive below. It is not alive in the middle. So 5 is interfering with 6 because right here, but not with 7. And then 6 interferes with 7, and it's a triangulated matrix, so I don't report the other direction in the accumulated matrix. So there's your interference graph as a pile of bits. This just walks the pile of bits, and add neighbor throws them onto, puts them in an adjacency matrix, because the next step, the coloring, wants them in an adjacency matrix. So if we go look at the live ranges, I have them in this array. Here they are. Live range 1 has no neighbors because it's going to be just converted to live range 2. Live range 2 has a neighbor of live range 3. That's your adjacency list. 3 has neighbors, oh, a bunch. 2, 4, 5, 6, 7. So it's no longer square. I'm going to list all the neighbors here. I'm not square, no longer triangulated. It's a square list. Every neighbor is mentioned everywhere. 4 is got 3, 4, 5, 6, 7, and so on and so forth. So that's your adjacency lists. Oh, see you, Cameron. Hey, enjoy your day out. And so now, having collected these, I'm going to ask the question, are you of low degree? And collect all my low degree guys and see how they color. So I just whip down to the end because low degree is this easy question. And that turns out to be everybody. I believe I got everybody in one pass. Oh, maybe I'm missing one person. Who didn't color in one go? Live range 6 may fail yet. Live range 6 has 1 allowed color, oh, and 4 neighbors. 3, 4, 5, 6, 7. So in order for live range 6 to get xmin 0, 3, 4, 5, 6, 7, 3, 4, 5, 7 have to not take 0. So this guy is not colorable trivially. Everyone else is colorable trivially. They have 15 float values, so they're done, or live range 1 has no neighbors, so he can just take RDI and he's all happy. So we're going to roll down the line until we get to some neighboring games here. So pull a dude off the list. I pull live range 1 off. It's trivial. He has no neighbors, nothing. I pull off live range 2. Live range 2 is trivial. He has a neighbor. Who's his neighbor? It's live range 3. So these two, I'm going to go to live range 3 and pull the neighbor out of him. That's this remove compress. So live range 3 has his neighbors, a bunch of folks, but he also has live range 2. So I claim live range 2 is trivial. He'll get a color. So since he's going to get a color, I'm going to pull him on the graph. When I pull him on the graph, I remove the edges from 2 to 3 and 3 to 2. Okay, by pulling 2 out, I've claimed I've pulled all the edges for 2 out in one shot. But now I need to go to the 2's neighbors, which are 3, and pull 2 out of 3's list. So compress here says pull it out of the list. So if I go look at 2 and I go to see his neighbors, he's got 3. If I go to his neighbors, though, his neighbors no longer have 2. I yanked it. And this code down in here happens if you remove so many neighbors that you became low degree. And that's the excitement part that lets live range 6 eventually color. So that was 2. He had no more neighbors. I'm going to the next dude out. I pick up what, live range 3 now. He's got a bunch of neighbors. So let me go look at them. So he says, I'm a neighbor to live range 7. I'm going to yank. I'm a neighbor to 4. I'm going to yank. I'm a neighbor to 5. I'm going to yank. I'm a neighbor to 6. I'm going to yank. So let's go look. Here's 3. He has all these neighbors. One of them was 6. I go to 6. 6 now has 3 neighbors. 6 had 4 before. Now 6 only has 3 neighbors because I've been reducing the graph. Going again. I pull off live range 4. I'm going to be a little quicker here. Pull some neighbors from 4. There's another neighbor to 6 again. Boom, boom, boom. Okay, so I did 4. Now we're going to pull 5. 5 has a neighbor 6. And we're done. And now I'm picking the next guy. Oh, it's 7. 7 has a neighbor 6. I pull it. Wait, I just hit this code. What happened here? This meant live range 6 lost his last neighbor. His neighboring list went to 0. And that means since he has 0 neighbors, he can always get x min 0. No one will take it away from him. And because we're doing this in a stack, when we unwind, 6 will get his first choice. He's the first choice. He gets x min 0 when he gets his choice. So pull things out of the color list. I'm all done. The color list now comes through and says, grab the next guy. Oh, flags. I thought I was done. No, here we go. Now live range 6 come off. And here's the trick. S pointer was not equal to work. So I didn't go to the pick a risky color. I'm guaranteed I'm going to get a color in here. So no more neighbors for you, and we're done. Everyone came off the list. Now I have a stack of them. I'm going to go in reverse stack order, unpop the stack, and I pull off 6. Here it is on the left. He has a mask choice of exactly 1. Go get that mask. Go see if I have any neighbors that would conflict and take a color away from me. I don't. The mask is not empty, so I can have a color. I have only 1 color. It's the only choice I get, so I'm going to color you to x min 0. Register 16 x min 0. Done. Live range 6 got a color. So live range 6 get a color. Live range 6 get a color. So live range 6 it's the output, it's the guess. And here I divide the input. Oops, here I divide the input by the guess, and here I add guess and divide it by 2, by multiply by half. So it got a color, and it got x min 0. So he's all happy. That's the return. So I didn't need to put a spill to move it to x min 0. I could get it for the return directly. Let's grab another guy off the list. Here's live range 8 flags. Pretty easy, only choice, no conflict. He gets it, his flags. It's all happy land. Let's see. Let's do some breakpoints here. We will have no fails. So I'll also do down here in biased coloring in a minute. Live range 7 has some neighbors. What neighbors does he have? He has neighbor 6. So he can't use x min 0 because 6 has got it. So first thing I'm going to do is I'm going to reinsert the live ranges back so I can go find the other guy when it's time to go find the other guy. There's 7 and 6, fine. And then I'm going to go grab the live range I got from 6, which is register 16 x min 0, and clear it from my current mask. So my current mask now here no longer has x min 0. So Away we go. That's the end of that one. The mask is empty. Go pick a color out of it. The first one is XMM1. Go to bias coloring. Oops. Allow myself to use bias coloring. It's all very boring. Let's go see if we have any interesting issues here. I'm going to set some breakpoints if we get into any of these things here, because this will happen at some point. So I'm looking for splits involved in live range 7. There is a split. The split, did he get a register? The answer is not yet. I haven't colored him. So then I'm going to go recursively ask, so Mr. Split, if you were to get a register, you haven't yet, but if you were to get one, you would bias toward your input. And if I can follow that chain of biases up and pick a register that somebody else has already got, I can clean up the whole chain of copies and say, they're all just picking the same register and they're all just to themselves. So look at your input. It's a divide. It's not a split. This didn't work. So I didn't find a bias color. I'm going to do the same thing on the use side. And it's also going to fail for me for the same exact reason. I haven't colored anything yet. So he's going to run out and say, I got no interesting choices. I'm just taking my original one. Done. I pick XMM1. So live range 7 picks XMM1. And if I go look at my output now, oh, here's live range 7. He's got XMM1. I'm adding 1 and 0. It's my add with my divide and my guess, or I'm adding guess to whatever comes out of the divide, and then I'm multiplying, and I'm going to move it in case I have to compare. So there's some choices here. Like if I can pick 1 for V5, I'll get rid of this copy. And if I can pick 1 for V4, I'll get rid of that copy. So some things might happen here yet. Grab another live range. Live range 5. He has some neighbors. What's a neighbor? Live range 6. Okay, so you can't take live range 6's choice. That's his only guy. He picks 17 as his first choice. He's going to try biasing here. The bias guy says, I looked at a split on 5. It wasn't colored. I'm going to go again. It's now the mole. It didn't help me. I look the other direction. Finding use. Get a bias. Okay. So I have a split use. That live range for the split here wants live range xmem 0. Is that available to me? Do I have xmem 0? I do not. So I'm out of here. It didn't work. I go back to 17 as my first choice. So I picked first choice for this guy as well. It's actually not a bad choice. Which live range was I just doing here, actually? Live range 5. Oh, I've lost which one was 5. That guy hasn't been picked his color up yet. But he's got this. Oh, I haven't done it yet. Hey, try it now. Try now, brown cow. Yes, we're XMM1 here. Well, we have a copy to 1 to 0 that we couldn't manage to avoid. We do have a copy from 1 to 1 we're going to avoid. So a little bit of a copy removal happened there. Go again, live range 4. He's got a neighbor of 7. I can't take 7 because I've conflicted, so I'm going to yank him from his list. I got live range 5. Live range 5 is XMM1. I'll yank that. I got a neighbor, live range 6, XMM 0. I got no more neighbors. What I got here? So at this point, I've got 2, 3, 4, 5, but not 0 or not 1. So pick first guy. It's live range 2. Attempt to bias. Another copy involved. Did this split help? Didn't give me anything there. That split went to the I to F by the other direction. Look for bias 17. Can I use 17? No. Here's one of these. I can't do it again. So again, I have a conflict where I must have 2 copies here. This copy, and then I end up with this copy. This is going away. Here you have a copy up here because I'm taking the original guy, and I need two copies of the original guy because he's my original guess. So I need the original guy always, but he's also the first guess. All right, well, that was very boring. Here's live range 3. He has a bunch of neighbors. He has a neighbor for live range 7 who's already XM1. He's got a neighbor, what? Live range 4 who's XM2. He's got a neighbor live range 5 who's XM1. He's got a neighbor live range 6, XM0. Oh God, okay. So he can't pick 0, 1, or 2. He's not going to bias anything because everything's going to conflict. So he's just going to pick live range XM 3, 3. Go again. Who am I up to? Live range 2. 2 has a neighbor of 3. 3 picked XMM, what? 0, 16, 17, 18, XMM 3. That's his only neighbor. He can pick 0 or 1 or 2. So he picks 0, XMM 0, and he's going to attempt to bias. So first go didn't find anything, but he has an XMM2 bias. Is that allowed? It is. So instead of doing 16 or XMM0, he's going to do XMM2. So we come out of here, we pick 2 instead of picking 0. So that was the first time biased color actually did something. And we go look. And then this copy went away. I could have picked 0. This could have been a 0 to 0, and then 0 gets copied to 2, but no, I just went to 2 directly, and now the 2 copy goes away here. And we're basically done with allocation at this point, except for removing the dead copies. So what else we got here? Oh, RDI at the start of the world. I'm going to go quick through that one. He's going to pick RDI. Done. I finished. No failures. I can post color. I'm going to post. Take a look. Nope. How about now? Okay. So how do we do here? Well, we end up with 2 copies in the loop and 1 copy outside the loop. And if you go look at Clang-02, it's the same count. This is almost, the copies are in slightly different places, but it's almost identical to Clang-02. So I claim these copies really can't be gotten rid of in any reasonable way. That's it. Take your R, convert it to float next to M2, put the constant in the register so you can use it later, make a copy of the original R because that's your guess, move the copy around so I can have some spare registers, divide the original the original value by guess, save that away, add guess, divide by 2, compare. If equals, carry on. This will be, the final basic block cleanup will fix the equals test case, so it jumps backwards instead of forward and then back. And then you've already got the registers aligned for the next pass. So you've got XMM1 as your guess ready to go, and XMM2 is hanging on to the original value. And there you go.
Yeah, so I guess my other question would be that if we pick a register, how are we going to assign it to the machine node so that we can do the encoding? Because when we are doing the encoding, we need to know the exact register we need to use for the encoding.
Right. So,
Or
so in this case, the data is now available. We just have to go fetch it. The data is available in the live range, and there is a node to live range mapping. So if I go up here to Lurges, this is my node to live range mapping. So you pick a node, whatever node you want, you look it up in this table, and he says, I went to live range 3. And I go to live range 3, he's got a register 19. That's your map. That's your register for live range 3.
right, yeah.
And then encoding does what the encoding does. So he'll subtract 16 surely and get an XMM3, but then he'll pick an XMM load or whatever he's going to do to go get the 0.5. Here's the divide, and it's live range 4, and it's 18. That's XMM2. So that's it. He's been register allocated. Return, done. Register allocation is done. I'll do an allocation just so you can see what happens here, but it's the same. But I'm not going to step through it. I'm just going to go to the end. He says as he stops at all the breakpoints that I left behind. Oh, there's a union that actually happened. There was a real union find happen there. Million breakpoints, million breakpoints. Just run to the end. No, run to the end. More breakpoints. Run to the end. Not yet. Wow, put a lot of breakpoints. There's the end. What do we got here? Block code asm. Okay, so RDI gets copied, so I have a copy of it. Do some math. Shift by 8 and add 8. That's the size. It's fixed in RDI. So the original value is in RDI, unscaled. I need the scale value because I'm claiming that my allocation call is basically a malloc or a calloc. It's a zeroing malloc call. He takes a first argument of the size. That's RDI. Well, the incoming function had RDI, so I had to move it. Okay. I claim it has to be unsigned. I'm going to force it. It's a 32-bit unsigned value. And then I'm zeroing out because I'm at my first loop. This is I for I equals 0 to array length. And I took the 0 and put it in RCX. I'm not sure why. Oh, I need another 0 because I'm going to do something with it. Why do I need another 0 there? That's interesting. Here is the first loop. And see if you're done. So it's a test first, I less than length. And if not, store I into I times scale plus offset plus blah, blah, blah. What happened here? Somebody's probably chat leaving, getting time. Yeah, I have to drop city author. And increment, that's actually an increment. So it'll be the short x86 increment instruction. And that's it, just a tight loop. So there's no loop ops, or I would have rolled this loop to put the branch at the bottom. So at some future simple date, simple will roll this loop around. Otherwise, you have a jump at the bottom of the loop to the top. And if you roll the loop once, you don't. Um,
Yeah, so
track.
how are we planning to add floating numbers to the calling convention? Because I think when I last time edited, you got rid of it because you said that you want to add it to the
Yeah.
basic machine.
Yeah. I was just hacking it this morning and I got it cleared out in chapter 19 and didn't get it moved up to chapter 20. And I had all kind of conflicts with chapter 19 and 20. So I was screwing around with that. Let me actually look at and then you can't tell which one. Yes, here we go, this one. Okay, so call in arg, no, how about call in mask is the common one here. Call in mask takes a function pointer so that you can do something with the argument types. And then I look at the calling convention and I pick up one of these two register mask lists, and that's the system v mask or the system v mask or the Windows mask. Where's the Win mask? Here's the Win mask. So I pick up this pile of masks. That just says if you're not a float, you're one of these, according to whatever, until you run off the bottom and then you're on the stack. Same for System 5, I believe. So I come through here, and this is kind of crappy code, but it's not terribly stupid. There's a 0 and 1 never count for indices, and you won't get past them. If you're after the end, I have to pass you a stack slot, which I haven't put in, but that's just a mask with a register number that's past the end of your other registers. That becomes a stack slot. Then I ask, are you a float? If you are, then I do the float thing. And there's the bias by 2 throughout here. And otherwise, I'm taking your calling convention argument. So an XMMS 0 here, this is the same for both System 5 and Windows, and it's just 0, 1, 2, 3, 4, 5. It's just and then it's just this, it's these guys in a row, XMMs. So back down here, what really happens is if you're coming in as a parameter to a function or a call argument, you'll be passing in the function pointer, which is used for the signature type, and which argument in question. You grab the calling convention, you do some range checks to decide that you pull in one of RDI, RSI, whatever mask. Or if you're a float, instead, you're going to pull up the matching float number. Now, this is my implementation of these ABIs, but I didn't look close at the ABI to make sure that's actually how it works. So I know in times past, like the early versions of Hotspot, the floats are packed into the int registers. And so you would stack them in, and but you also did even odd for long and doubles and things that all cleaned out when life got better and 64 bits showed up. But the flexibility is here to say I can pass it like in this particular calling convention for Windows, they only ever want to pass four registers. It's XMM 0 through 3, or it's the four they list above. So that if they were to do some sort of context switchy thing at a call site, they only had to stack or they only had to save 4 or 8 registers or something. I found the reasoning kind of facetious. I didn't get it. It made no sense to me. If I'm passing 4 ints and 4 floats, why not use 8 registers, 4 int registers and 4 float registers? Okay, why not use 10? Why not use 20? Why are we limiting ourselves here to any number of registers? So like the Java convention, you want to pass more registers? Pass more registers. Pass them to you right now. You got, 16 int, 16 FP. You can pass 32 values in a Java C2 call, and he'll just stack them in registers. Great. You go past that? Yeah, you go on the stack. But if you got registers to spare, you do. Use them. Make no sense. Fine. So, but the other piece of that is, of course, the calling convention for the JIT can pick, he has both sides of the equation, so he can pick whatever he wants. So he has callee save and caller saves, unless you have so many arguments that you need to burn into the caller or callee saves, and he burns into the caller and callee saves. That's fine. So we can be system 5. We can also only be system 5 when we're calling native code. But if we're calling simple to simple, we can be our own calling convention here. So there is System 5 and Win, that these are all like how you call native. But there is another calling convention, which is how simple calls simple code. And like I said, you can do anything you want there.
Yeah, so how should we encode the floating constant? So, because I think last time we decided to add it to the integer register, the GPR, and then we said that we're gonna do
Yeah.
splitting, I think, in the
Yeah,
register
yeah.
allocation.
Right. So I took it as it stands right now. There is another version of the universe where we change this guy. Um, oh, he's claiming he's an X mask. Yeah. So if we make the float x86 be an immediate float value in an integer register, then the register allocator will say, well, you produced the value in the int register, you need it in a float register, I have to move it. He'll put a split in. The split has to move from int to float. Well, you can do that on an x86. So, okay, fine, you do. So you get an insert, you get a, int to float move.
Yeah, so if it's not a constant, we are just using a wider bit mask, I think. So basically we have a bit mask that has like 40, no, I think 64 bits, and then we're just reusing that later.
Right. So you said something was a little odd. If we're the constant on one side, currently we're setting it into an XMM directly. I don't know if that x86 instruction exists.
No, if you have a float number that's not it's not a constant,
Yeah, if you
we're
have a
just
float
gonna.
number, then you've got it computed somehow, typically in a float register.
So how are we gonna fix that? Like what instruction are we going to use to load a float into a int register then?
Well, why are we moving a float into an int register?
Well, we have to find a way to. Well, we are not moving it into that because I think we said that if you load it into
Yeah,
a
it's like you're
GPR,
confusing yourself here.
yeah. Because if you load a float constant into an integer register, then we're gonna be able to load it into a
Yeah,
float
we're going to
later on.
use a split. The split's going to claim that he has full register mass, and he'll take it in an int and produce it in a float. That's how the allocator is going to do that. He's going to say, oh, I need a split here. And it'll do the job. Then you ask the split, Mr.
Yeah.
Split, encode yourself. And he'll say, well, I have an int register on the left and a float register on the right. I must be one of these funny x86 int to float register moves, which I'm pretty sure exist.
Yeah. So how are we gonna do the code emission? So if we have all the encoding done and we have like a byte stream, are we just gonna use a an object file exporter, or how are we going to go about generating the executable?
Yeah, right. So that's sort of future simple problem. The easy one to get going here is just throw the encodings in a byte array stream. It's just a big array. You're just going to write to an array, pick up the encodings. We need some metadata to go with that. That'll be anything that needs a runtime relocation. We'll probably want all the function entry points as a table mapped. We may, on the RISC side, put the floats in the encoding stream. So they have to be landed in a spot that's not going to get executed, and then need some sort of, rip relative addressing mode. So there's a couple choices. It might vary by architecture. We're going to need an encoding, basically an object file, an in-memory object file representation. The encoding will be one piece of that. The relocation information will be another piece of that. Entry points for functions will be another piece of that. And then we can go ask, what's the goal here? If the goal is to run a JIT, that's it. You got enough information. You throw that code into a code cache, and you can just jump to it and execute, and away you go. It's all good. If you want to write it to disk, you might want to pick a format. The format's probably, say, ELF, but it could be, some dwarf subset. If it's hugely fancy and we have to do all kinds of things, you might go find an ELF format writer. But if it's really simple, we'll just go write an ELF format ourselves. There'll be like some magic headers in the beginning, some magic bits to set yourself up, and then you'll slap down bytes for the actual code and bytes for the relocation data, and you're done. And I've done these things before, old versions of ELF and prior things from time before. These are not hard if you don't do anything weird. So if you want 1,000 tons of debug info, and you're like dwarf for the lose or dwarf for the win, I don't know. Well, okay, now you got a harder problem. Right now, we don't have any debug info. Some future date, maybe we have panics that have full debug state and we have debug info. Or we have debug info that we allow breakpoints so you can do like Java does and have optimized code and set a breakpoint, stop, then flip execution strategies from JITted code to some sort of C of nodes interpreter and have full debug info and be able to single step simple code and then hit continue and go back to full speed execution. These are all doable things with more work. But for your first cut, I would just fill the encoding stream. If you want to do the encodings, go for it and fill the encoding binary stream with bits. And then we'll fold that into a larger structure, which will be what eventually will become an ELF file or disk file writer of some kind.
Yep.
Okay. Anyone else want to ask questions about register allocation? Encoding? I know Matt was very curious about what it took to have a portable allocator. Here's a question. Here we go, live demo time. We'll do this thing here. And I haven't tested, so this may fail miserably. Let's try again. Okay. Argument A0, move it to a float, load an immediate into A0, register A, whatever that is, and move it to a float. So here is exactly what you're talking about. We put an immediate value in an integer register, move to a float. Bonus extra copy because, here we are in the land where you just have to have a copy. And then here's my guess in F0. And make a copy, go divide. There's the other copy, multiply, add, multiply, compare, branch, yada, yada. This got 2 copies here and 2 up here, but one of these came because I did this hack. So same count of copies minus the float in an int register copy. So that's RISC-V. So I claim no problem, but either way.
We need to update our assembly output to look like this. It's so much better.
Oh yeah. Yeah. I've been going back and forth between, what you and I are doing and simple and picking and choosing what works best.
Yeah.
we'd be yes, I think we'd be very happy with this kind of output. And it's not hard to do. So there's
Yeah.
a thing there.
Yeah.
Boom. So I claim RISC-V also compiles Newton just fine. Actually, then the next one is do a, let's see here. This guy has an allocation. So let's go do this guy. Oh, it's a to do. There you go. All right, there's the fail. So the store risk has a to do, so we're not done. Um, that would be the value. He needs another register. Oh, because on the x86 side, I picked up generically the addressing mode piece of things. I think. Why did this guy not pick up? Because he didn't implement, he just overrode him. Fine. Sure
Yeah,
enough.
so yeah, so what's wrong with this again?
Well, I is 3 here. And then we hit the to do. So what is the allowed set for the third argument to the RISC store, to the store op? His inputs are control, memory, the pointer, so that is the allocation from the array of int, the offset piece, which is another register, because we're not doing a base plus offset, we're doing red plus red, and an immediate one. So the claim here is this is probably any integer register. And then this is another register. So, oh, it's a 3 register guy. Sure. Base, offset, another register. Although this probably should have been folded into a store immediate on a RISC, which I don't know that RISC-V has one. So RISC-V is base offset. I bet you they do reg plus reg. That's really common. So we'll throw in those and see what happens. Here we go again. Now we hit another one. Outreg on the new. Okay, what is the output for the new? I have to go do a projection thing off of the same as the new x86. It's going to be this guy. Not this guy. This guy. Except the RISC version. And he should say, I have outputs and projections, right? Yes, so he should say no. And then the next guy chokes. Oh, he doesn't need to. Round 7. Okay, so that means he spilled forever without making progress. So he had something else going on that he spilled forever. We'll go back to my new here. I would have expected him to come in here, which maybe he did. No. All right, so I have some other failure going on. So the RISC-V isn't, I knew the RISC-V had issues, and I was just recently doing calling things. So the calling convention on the RISC-V is not there. And that's why we're in endless allocation land. And we can probably even figure out why it's endless allocation. The first round of fails says something with no registers. Live range 11 has no registers. Still has no registers. Okay, we're not making progress on spilling. So live range 11 has no registers. And we get a not implement when we try to dump because somebody didn't print. So I claim not worth doing it live. Yeah, this guy won't print, so I can't debug. So there's their current state of the RISC port is missing a bunch of things and not doing calls. So things to do. And Tomas, you probably figure out the RISC op here and go figure out all the to-dos until it gets to where it's otherwise not allocating. I can do this dump if it'll let me stretch the window. And he said, but I don't know where live range 11 is now. That's the fail here. But here is and mask, shift left, immediate add. This is, go compute array length, which is, 32. He knows the array length is 32 directly. Oh, that's nice. And then there's some more shift mask operations because he doesn't have a scaled shift add baked in like an x86 does, baked into a store. So store 4 is going to be the length. Store 8 will be the other store that's in the original test case. Here, he makes an array of like 3 elements, which is 24 bytes because they're 8 bytes each plus the array length. Then he stores at arg and loads at arg and mast. So you expect to see a shift by arg and add it to the array base and a shift after and masking. And I saw all those ops. So the ops are all there, but they're not getting allocated because the registers aren't picked right for something. That's forcing a hard conflict that he can't resolve. Standard failure for mid-port, or the RISC instruction coding probably is all there. The RISC register allocation is not all there. And that's fine.
So what else would I need to add? Would I need to add something to the load instruction or?
Well, I would start by saying, go run test alloc2, it will crash. Go ask, go do this print, the nice ASM print, it will crash. Go figure out why this crashed. And it's because, load, not yet implemented, it's because the load, wherever I lost my load up here, isn't printing. Go make that print just like x86 prints.
Yeah.
And then you'll probably find the store won't print. Oh, okay, you'll pick 3 or 4 of those, they'll print finally. Then you can get a register allocation dump after he decides he's spilling register live range 11. Now that he's spilling live range 11, you have to go figure out why did he not allocate live range 11? Why did he spill it? He probably spilled it right away. If he spills it right away, it means, oh, he's splitting it and he's not making any progress. Somebody is trying hard to say, I need to move this from here to there, but I can't. Or the split op on the RISC has the wrong mask, or I don't know what. Something happened wrong. Now I can't tell you. You have to go diagnose, or I'll diagnose when I get a chance.
Yeah.
And then that's sort of the race is on. The prints are easy and quick, and I'll probably do them as fast as I can when I'm done with today. And the storm passed, so I'm going to go walk about my house and do damage control and things like that will happen. I may or may not get to it today. So if you beat me to it, you do. And if you do, just throw it on Discord and say, here's your PR, and here's some stuff. And I'll take a look.
Right.
Yeah. Okay. Anyone else want to say anything, ask anything? I'm gonna bail in a second here. All right, I think we're done. Stop share. There goes. And until we meet again. Bye-bye.
Bye.